Babylon, June 10th, 323 BC. Alexander the Great is 32 years old and dying in his tent. He has spent the last 13 years turning himself into the largest empire the world has ever seen. Greece to the Indus River, and he still has plans. Arabia, Carthage. His maps are on the table beside him. His generals are outside waiting for orders. He has been running a fever for 11 days. It comes in waves, cycling roughly every third day. Chills so violent his teeth chatter, then heat so intense he shakes in his own sweat. His personal physicians have no idea what it is. What nobody in that tent knew was that the young king was being killed by an organism smaller than a red blood cell, delivered by an insect no bigger than a grain of rice, carrying a parasite that would go on to kill more human beings than every war in recorded history combined. Reshape the boundaries of empires, rewrite the human genome itself, and, right now, in 2026, still take a child's life somewhere in Africa roughly every minute. That parasite is called Plasmodium. The disease is malaria. And the story of how something too small to see with the naked eye became the deadliest killer in human history starts not in Babylon, but 9,000 years earlier, in a rainforest at the edge of Central Africa. Somewhere in the tropical lowlands of what is now Cameroon, around 8,000 BC. A silverback gorilla is sitting in the dappled light of a rainforest clearing. A female mosquito lands behind his ear, drives a needle-thin proboscis through the fur, and drinks. She's looking for the blood meal she needs to feed her developing eggs. When she flies off, she carries away something the gorilla's ancestors have been playing host to for hundreds of thousands of years. A single-celled parasite, riding quietly in the blood. That mosquito never lands on a human, nor does the next one, or the 10,000 after that. Gorillas and humans in this era mostly do not share the same forest edges. What changes? What will eventually turn a small primate infection into humanity's deadliest disease is us. Around this same window, human beings in West and Central Africa begin doing something new. They begin clearing forest for cultivation. Standing water gathers where it never gathered before. Mosquito populations explode. And humans and gorillas, for the first time in evolutionary history, start living close enough together for one insect to visit both. Somewhere in that overlap, on an unremembered afternoon, a single infected mosquito bit a human being. The parasite made the jump, and it was never going to leave. For most of prehistory, after that first jump, malaria stayed a mostly African disease. It needed two things to travel: the right kind of mosquito and human beings, dense enough to keep the transmission cycle going. Both of those conditions arrived together the moment humans began building cities. Ancient Egypt is the first civilization we can prove malaria reached. In 2010, a team of researchers led by Zahi Hawass in Cairo pulled DNA out of the mummy of King Tutankhamun, the boy pharaoh who died at 19 in 1323 BC, and found the genetic signature of Plasmodium falciparum, the deadliest strain of malaria. He wasn't the only royal. The mummies of two of his relatives tested positive too. Egyptian medical papyri from around 1500 BC describe recurring fevers with distinctive cycles, prescribe rituals against them, and hint that the sickness came from something in the marshes along the Nile. By the time the Greek physician Hippocrates was working on the island of Kos, around 400 BC, malaria had names, several of them. He described what he called tertian and quartan fevers, fevers that returned every third or fourth day, the exact rhythm produced by different Plasmodium species, as they burst out of red blood cells in synchronized waves. He noticed that people who lived near stagnant water were far more likely to fall sick than people on higher ground. He didn't know why. He guessed it had something to do with the air itself, an idea that would stick for the next 2,000 years. On the other side of the world, the Chinese medical text Ne Ching Su Wen, dating to roughly the same era, describes the same cyclical fevers and the same connection to standing water. Chinese physicians independently arrived at similar treatments, herbal preparations from a plant called Qinghao or Artemisia annua, a name that will matter enormously in this story, but not for another 2,500 years. By 300 BC, malaria was quietly established across Egypt, Mesopotamia, the Eastern Mediterranean, India, and China. Physicians could describe it. Priests could pray against it. Nobody could stop it. And by the time a young Macedonian king rode into Babylon at the head of the largest army in history, the disease was already waiting for him in the marshes along the Euphrates. Alexander did not have to be in Babylon. He had chosen to be. After 13 years of continuous campaigning, through Persia, Egypt, into India, he had returned to make Babylon the administrative capital of his new empire, a decision his advisors urged him to reconsider. Babylon in June was hot, humid, and ringed by marshland, the exact conditions the Anopheles mosquito preferred. Historians have argued for centuries about what exactly killed him. Ancient sources describe a banquet at the home of a friend named Medius, a cup of wine, and a fever that began that night and worsened over 11 days. Some later writers suggested poison. Others pointed to typhoid, West Nile virus, or the sheer accumulated damage of years of hard drinking and battlefield wounds. The most detailed modern analysis of the surviving accounts, a study by David Oldak and colleagues published in 1998, concluded that malaria, most likely Plasmodium falciparum contracted from the Babylonian marshes, is the single most plausible cause. It is not proven. But it fits the fever pattern, the season, the geography, and the timeline better than any alternative. Whatever killed him, the consequences of that death rewrote the ancient world. Alexander had no clear heir. When his generals asked, on his deathbed, who should inherit the empire, he reportedly answered, "To the strongest," a phrase that guaranteed exactly what happened next. Within a year, his generals, men like Ptolemy, Seleucus, Antigonus, and Cassander, had turned on each other in a series of wars historians call the Wars of the Diadochi. Those wars ran for the next 4 decades. When they finally ended, Alexander's single empire had shattered into 3 permanent kingdoms: the Ptolemaic dynasty in Egypt, the Seleucid Empire in the Middle East, and Antigonid Macedon in Greece. That would shape Mediterranean politics for the next 300 years. An empire built by one of history's most talented military commanders came apart because that commander drank untreated water, slept near a marsh, and got bitten by an insect too small to appear in a single one of his biographies. If malaria really was the cause, and every modern study of the evidence puts it at the top of the list, then it was already, by 323 BC, quietly shaping world history in a way nobody watching would think to record. It was about to do it again. Bigger. And this time to a civilization that would give the disease its modern name. Rome's relationship with malaria was different from Alexander's. It didn't kill Rome in a single night. It bled Rome for 1,000 years. The Pontine Marshes sat directly south of the city, a broad stretch of low-lying wetland along the Tyrrhenian coast, perfect Anopheles country. Every summer, as temperatures rose and the marshes filled with breeding mosquitoes, waves of fever swept through the city and the surrounding countryside. Roman writers noticed the pattern early. The poet Horace complained about the unhealthy season in Rome. The physician Galen cataloged the different fever cycles the same way Hippocrates had. And Roman farmers, generation by generation, quietly abandoned the countryside around Rome itself, leaving vast stretches of the Roman Campagna, some of the most fertile land in Italy, empty. Not because the soil was bad, because working it was a death sentence. The Romans had a name for the sickness. They called it malaria, bad air, from the belief, still centuries away from being disproven, that the disease rose off the marshes in a poisonous vapor. That name, malaria, survived every empire that came after Rome and eventually became the modern English word, malaria, for the disease itself. Roman emperors died of it. Popes died of it. An estimated 4 popes across the medieval period alone, sitting in a city surrounded by malarial swamps that no engineering project of the era could drain. And Roman generals fell to it in numbers that historians still argue over. Some modern researchers, the historian Robert Salares, chief among them, have argued that recurring malaria epidemics in the late imperial period contributed to Rome's declining population and made large parts of Italy easier to invade. Whether malaria actually helped bring down the Western Roman Empire remains one of the most contested questions in ancient history. What isn't contested is that malaria was there, killing continuously. Throughout every century, Rome existed as a power. This decision, the Roman decision to build and hold a capital next to a permanent malarial marsh, seemed reasonable at the time. It was not. Every emperor from Augustus onward inherited the same problem the geography came with, and none of them ever solved it. If this is the kind of history you want more of, subscribe. We cover the diseases that decided who held power every week. Now, from a single marsh outside Rome to an entire continent, Europe could not safely enter, because by the 1800s, malaria was the wall Europe couldn't climb. For most of European colonial history, one continent stayed effectively closed to European conquest. And it wasn't because the people who lived there were better armed. It was because the mosquitoes were. West Africa in the 18th and 19th centuries earned a nickname among European sailors and soldiers that stuck for 200 years, the white man's grave. The reason was simple arithmetic. Death rates among European soldiers stationed in the Gold Coast, modern Ghana, ran, according to British military records from the 1820s, at roughly 400 to 700 deaths per 1,000 men per year. Read that number again. In some years, more than half of every European regiment sent to West Africa was dead within 12 months of arrival, almost entirely from malaria and its frequent companion, yellow fever. The Royal African Company, a British trading corporation, sent 1,240 employees to its West African stations between 1684 and 1732. Of those, 653 died on station, a death rate of just over 50%. And the survivors were, in many cases, permanently debilitated by recurring fever. That mortality rate is why the interior of Africa remained, on European maps well into the 1850s, largely a blank space labeled unexplored. Europeans could hold coastal trading forts, Elmina Castle, Cape Coast Castle, Fort James on the Gambia River, but they could not push inland in force. The first serious European attempt to map the Niger River, led by a Scottish explorer named Mungo Park in 1795, killed nearly every man on the expedition, including Park himself on a second attempt in 1806. The pattern repeated. Alexander Gordon Laing, the first European to reach Timbuktu overland in 1826, died within weeks of leaving it. David Livingstone, the most famous African explorer of the Victorian era, died of malaria complications near Lake Bangweulu in 1873 after decades of chronic infection. Meanwhile, on the other side of the Atlantic, malaria was doing the same work in the opposite direction. The transatlantic slave trade, a system that forcibly transported roughly 12.5 million people from Africa to the Americas, carried an unexpected genetic byproduct with it. Many West Africans, as we'll see in a later chapter, had partial genetic resistance to malaria that Europeans did not. That difference in mortality became, for European planters in the Caribbean and the American South, one of the darkest justifications for continuing a system already being challenged on moral grounds. Africans, planters argued, could survive in the malarial swamps of coastal Georgia and the sugar plantations of Jamaica. Europeans couldn't. The truth of that biological difference, a truth we now understand at the molecular level, did nothing but deepen an atrocity. The mosquito that had killed Alexander and emptied the Roman Campagna was now, effectively, dictating which populations could be moved where and under what terms. And Europe, for the first time in 3 centuries of aggressive colonial expansion, had run into a wall it could not force its way through. Somebody was going to have to find a way around it. The way around it came, as so many colonial-era medical breakthroughs did, from indigenous knowledge Europeans initially had no interest in taking seriously. In the highlands of what is now Peru and Bolivia, the Quechua people had known for centuries that the bark of a particular tree, a small evergreen the Spanish would eventually call cinchona, could reduce fevers. They ground it, boiled it, drank the bitter infusion. What Europeans arriving in South America in the 16th century didn't initially realize was that the compound in the bark, later isolated and named quinine, happened to be one of the few substances in the natural world capable of killing Plasmodium parasites inside human blood. The bark reached Europe in the 1630s, carried across the Atlantic by Spanish Jesuit missionaries, which is why for the next 2 centuries it was widely known as Jesuit's bark or Peruvian bark. According to a story repeated in nearly every popular history of the drug, the bark got its European name from the wife of the Spanish viceroy of Peru, the Countess of Chinchon, who was supposedly cured of a malarial fever by it in 1638. Modern historians have looked hard at that story and concluded it is almost entirely apocryphal. The Countess in question died before the supposed cure, and the story doesn't appear in any European sources until decades later. But by then, it didn't matter. The tree was named after her, regardless, Cinchona officinalis, and the myth stuck. It's a good reminder that a great deal of the popular history of medicine turns out, on closer inspection, to be more legend than fact. What isn't legend is what the bark actually did to European power. For the first time, Europeans stationed in tropical regions had a treatment, imperfect, foul-tasting, expensive, but real, that could keep them alive in places where malaria had previously killed them at catastrophic rates. British administrators in India began taking it daily, mixed with sugar and gin, a combination that eventually gave the world the gin and tonic. Dutch colonial officials in the East Indies set up a monopoly on cinchona cultivation on the island of Java, growing the trees in vast plantations and, by the early 20th century, supplying more than 90% of the world's quinine. Ronald Ross, the British Army doctor who will show up in this story shortly, wrote in his memoirs that quinine was the only drug the empire really relied on. Without it, the second half of European colonial expansion into inland Africa, into Southeast Asia, into the swampier parts of India and the Pacific would have been medically impossible. With it, an empire on which the sun never set was, at least in part, held together by a bitter powder from a Peruvian tree. But quinine had a ceiling. It could suppress the fever. It could not eradicate the disease. And to understand why, to understand what was actually going on inside a human body during a malaria infection, you have to look at something no one in the entire history of the empire could see: a parasite in the act of killing you. To understand what makes malaria different from every other disease in this series, you have to look at what actually happens inside a human body during an infection. And to describe it, we have to start with a bite. A female Anopheles mosquito lands on your arm at dusk. Only females bite humans. Males feed on plant nectar. She drives her proboscis through your skin, injects a small amount of saliva as an anticoagulant, and begins to feed. In that saliva, invisibly small, are thread-like parasites called sporozoites, Plasmodium at its infectious stage, having lived, until this moment, in the mosquito's salivary glands. She injects perhaps 20 or 30 of them into your bloodstream. She flies away. You never notice. Within 30 minutes, those sporozoites have traveled to your liver. There, they invade individual liver cells and begin doing something extraordinary. Each sporozoite starts multiplying inside its host cell, one becoming thousands, until the liver cell can no longer contain them. It bursts. Waves of a new form of the parasite, called merozoites, pour out into the bloodstream. Depending on the species, this can take days, or in some cases, months. The merozoites then do it again. Each one finds a red blood cell, invades it, feeds on the hemoglobin inside, and multiplies. The red blood cell, packed with new parasites, eventually bursts too, releasing more merozoites, which invade more red blood cells, in a cycle that repeats every 48 or 72 hours, depending on the species. That synchronized bursting, millions of cells rupturing at once, is what produces the classic malarial fever, the wave of chills followed by intense heat that Hippocrates described in Kos 2,500 years ago. There are 5 species of Plasmodium that infect humans. Plasmodium falciparum is by far the deadliest, the strain that killed Alexander in Babylon, that killed Tutankhamun in Egypt, that still kills the overwhelming majority of the roughly 600,000 people who die of malaria every year today. Plasmodium vivax is more geographically widespread but usually less lethal. Plasmodium ovale, Plasmodium malaria, and Plasmodium knowlesi round out the list. The reason falciparum is so dangerous is that it does something the others don't. The red blood cells it infects become sticky. They cling to the walls of small blood vessels, especially in the brain, blocking blood flow. Untreated cerebral malaria has a mortality rate above 20%, even with modern intensive care. And the disease can kill a healthy adult within 24 hours of the first symptoms. For most of human history, none of this was known. To Hippocrates, to Roman physicians, to the men trying to treat Alexander, it was simply a fever from bad air. The idea that a mosquito bite, a liver cell, and a red blood cell were involved in any of it would have sounded, in every century up to the 1890s, like fantasy. There is one more thing malaria has done to the human species. And unlike the deaths, unlike the fallen empires, this one is written, literally, into the DNA of 500 million people alive right now. The parasite has been killing humans for so long, in such numbers, that it has done something no other pathogen has ever done. It has rewritten our genome. Malaria is the strongest documented selective pressure on the human species, and you can still see its fingerprints in the blood of anyone whose ancestors came from a malarial region. The clearest example is sickle cell trait. In 1949, a young English geneticist named Anthony Allison, who had grown up in Kenya and returned there to do field work, noticed that a mutation in the hemoglobin gene appeared at strikingly high frequencies in East African populations. Carrying one copy of the mutation, he found, gave a person substantial protection against falciparum malaria. Carrying 2 copies, however, produced sickle cell disease, a painful, often fatal blood disorder in which red blood cells collapse into rigid crescent shapes and clog small blood vessels. It was one of the first clear examples in medicine of what geneticists call a heterozygote advantage. A mutation so dangerous in double dose and so protective in single dose that natural selection had kept it circulating in African populations for tens of thousands of years, doing brutal arithmetic on generations of children. Sickle cell is not the only one. Glucose 6-phosphate dehydrogenase deficiency, or G6PD deficiency, is a genetic condition that affects roughly 400 million people worldwide, concentrated across Africa, the Mediterranean, and South Asia. And it, too, provides partial protection against malaria. beta thalassemia and alpha thalassemia, blood disorders found across the Mediterranean, Middle East, and Southeast Asia, follow the same pattern. Duffy antigen negativity, a genetic variant that makes red blood cells resistant to Plasmodium vivax invasion, is present in nearly all West Africans and almost no Europeans. Add all of it together, and you get roughly 500 million people alive today, carrying a genetic mutation that exists because malaria killed off the ancestors who didn't have it. That is not a metaphor. That is measurable evolutionary pressure, still visible in living blood samples right now. No other single infectious disease, so far as anyone has been able to prove, has left a signature like it on the human species. Malaria didn't just kill people, it selected which people lived long enough to reproduce. And it has been doing that quietly for at least 10,000 years. But by the late 19th century, that arrangement was finally about to change. Because for the first time in 10,000 years of malaria killing humans, one human was about to figure out exactly how the killing worked. Ronald Ross was, by most accounts, an unlikely hero for the story of malaria. He was a moody, difficult man, a poet by aspiration, a surgeon by his father's demand, an officer in the Indian Medical Service by economic necessity. In 1894, he had begun exchanging letters with the eminent Scottish parasitologist Patrick Manson, who had suggested, based on his own work with a different tropical disease, that mosquitoes might somehow be involved in malaria transmission. By the summer of 1897, Ross was working out of a small hospital laboratory in Secunderabad, in southern India, with almost no equipment, in temperatures that regularly climbed above 100 degrees. He had been dissecting mosquitoes, hundreds of them, then thousands of them, under a microscope, looking for any sign of a malaria parasite. He had found nothing. On August 20th, 1897, Ross dissected a female Anopheles mosquito that had, days earlier, fed on a patient with active malaria. In the wall of the mosquito's stomach, he saw something new, a cluster of pigmented cysts, exactly the kind of structure a developing Plasmodium parasite would produce. He had, without being able to prove the full life cycle yet, found the missing link. Mosquitoes were the carriers. He wrote a short poem about the discovery that night that is genuinely worth looking up. In 1902, Ross received the Nobel Prize in Medicine for his work. He was only the second person ever to win it. What Ross's discovery unlocked was staggering. If you could kill the mosquitoes or prevent them from breeding, you could break the malaria cycle without needing to cure anyone. The first serious test of that theory came, of all places, in Panama. The French had tried to build a canal across the Isthmus of Panama in the 1880s, under the direction of Ferdinand de Lesseps, the engineer who had built the Suez Canal. The project collapsed. Roughly 22,000 workers died during the French attempt, the majority from yellow fever and malaria. The jungle simply could not be tamed. When the United States took over the project in 1904, they brought with them an army doctor named William Gorgas, who had already led a successful anti-mosquito campaign in Havana. Gorgas drained standing water across the entire canal zone. He fumigated houses. He screened windows. He treated infected workers with quinine. The malaria hospitalization rate on the project fell from more than 800 cases per 1,000 workers per year to under 70 within a decade. The canal opened in 1914. Without Gorgas's work, and without the mosquito-borne transmission Ross had proved 17 years earlier, the Americans could not have finished it either. For the first time in human history, malaria was on the defensive. But the weapon that would push it further onto the defensive than anyone in 1914, imagined possible, hadn't been invented yet. And when it arrived, it would carry a very long shadow behind it. That weapon arrived, by accident, in 1939. A Swiss chemist named Paul Müller, working for the industrial firm Geigy, had been searching for a better insecticide to protect Swiss wool from moths. He rediscovered a compound first synthesized in 1874 called dichlorodiphenyltric chloroethane, DDT. In the field, it worked spectacularly. It killed mosquitoes, houseflies, lice, and Colorado potato beetles at trace concentrations. It appeared, at the doses used, harmless to mammals. During the Second World War, the Allies used DDT extensively to control lice and malarial mosquitoes among troops in the Pacific and Mediterranean theaters. Miller won the Nobel Prize in 1948 for the discovery. After the war, DDT went global. The World Health Organization launched the Global Malaria Eradication Program in 1955, spraying DDT across malarial regions on nearly every continent. And at first, it worked spectacularly. Malaria was effectively eliminated from Europe, the United States, Australia, and large parts of Asia within 20 years. Sri Lanka's annual case count fell from close to 1 million cases in 1946 to just 17 confirmed cases in 1963. Then, in 1962, an American biologist named Rachel Carson published a book called Silent Spring, documenting DDT's devastating effects on bird populations and other wildlife. The chemical was accumulating in food chains at levels that were rendering entire ecosystems sterile. The public reaction was enormous. The United States banned agricultural DDT in 1972. Country after country followed. And in country after country where DDT spraying had suppressed malaria, the disease came roaring back. Sri Lanka's 17 cases in 1963 became roughly 500,000 cases by 1969, one of the fastest recorded resurgences of any infectious disease in modern history. The lesson was uncomfortable. DDT had been genuinely dangerous for the environment. It had also been genuinely effective against malaria. Nobody had planned for how completely the disease would return the moment it was stopped. Malaria had lost a battle. It had not lost the war. And in a small research laboratory in Beijing, working under a code name assigned by Mao Zedong himself, a young Chinese pharmacologist was about to find the drug that would fight back. In 1967, at the height of the Vietnam War, malaria was killing more American soldiers in Southeast Asia than combat was. The North Vietnamese, fighting in the same jungles, were losing even more people. Ho Chi Minh personally asked Mao Zedong for help. Mao responded by launching a top-secret research initiative, Project 523, dedicated to finding a new anti-malarial drug that could work where quinine and its synthetic descendant chloroquine were failing, because Plasmodium falciparum was becoming resistant to both. One of the researchers assigned to Project 523 was a 39-year-old pharmacologist in Beijing named Youyou. She had trained in both traditional Chinese medicine and modern pharmacology. She began systematically screening ancient Chinese medical texts for any plant with a documented anti-malarial effect. In a 4th century document called The Handbook of Prescriptions for Emergencies, written by a physician named Ge Hong, she found a reference to sweet wormwood, the plant we met briefly all the way back in the Hippocrates chapter, Artemisia annua, and a specific preparation using cold water rather than boiling. That single detail, cold water, not boiling, turned out to be the key. Boiling destroyed the active compound. Tu extracted it cold, isolated it, and by 1972 had purified what she named artemisinin from the plant's scientific name. In animal trials, it killed Plasmodium at doses no other drug had matched. In humans, it worked within hours. Youyou received the Nobel Prize in Medicine in 2015, the first mainland Chinese scientist ever to win a Nobel in the sciences. Today, artemisinin combination therapies are the frontline treatment for falciparum malaria worldwide. They have saved, by conservative estimates, more than 7 million lives. And yet, malaria still kills roughly 600,000 people every year, the overwhelming majority of them children in sub-Saharan Africa. Resistance to artemisinin has already emerged in parts of Southeast Asia. Mosquitoes are increasingly resistant to the insecticides used on bed nets. The disease is not defeated. It has never been defeated. It is only, for now, held. Alexander the Great died in a marsh-ringed palace in Babylon and shattered an empire. Roman emperors died of the same fever, and the marshes around their capital emptied. Popes died of it. European soldiers died of it by the tens of thousands in West Africa. Enslaved Africans were forced across an ocean, partly because the mosquitoes on both sides killed Europeans and spared them. 500 million people alive today carry a mutation in their blood that exists only because their ancestors were selected, one dead child at a time, by a parasite too small to see. Ronald Ross dissected a mosquito in Secunderabad on a hot afternoon in 1897. William Gorgas drained the swamps of Panama. Rachel Carson wrote a book about birds, and a Chinese pharmacologist read a 4th century medical text and found a molecule that had been waiting there for 1,600 years. Not bad for a parasite too small to appear in any biography of any king it ever killed. And it's still out there right now, not in a museum, not in a history book. In the standing water at the edge of a rice paddy in Central Africa, in the wetlands of the Amazon basin, in the salt marshes of Southeast Asia, an Anopheles mosquito is landing on somebody's arm at this exact moment, driving a needle-thin proboscis through skin and injecting the same parasite that killed Alexander in Babylon 23 centuries ago. The disease is older than every empire in this video. It is still, by every measure that matters, the deadliest killer in human history. If this is the kind of history you want more of, smash that subscribe button. We cover the diseases that shaped history and decided who ruled the world. Drop a comment telling us which part of the malaria story surprised you the most: Alexander's fever, the white man's grave, or the parasite hiding in your own DNA. And if this video taught you something new, hit that like button so more people can enjoy it as well. The next video is waiting on your screen. I will see you there.